Thanks, Nicholas.
Go for it.
So following Nicholas's email, I'm going to introduce myself again. Did a PhD at the University of Canterbury down south. Worked on different ways of representing numbers in FPGAs to do fun stuff. So I tell lay people that I did a PhD in how to add two numbers together. Gets that response, but it is literally what I did. Moved to Hamilton and worked for a company called Endace. They do networking stuff, capturing packets. I don't know, is it a digital twin of your network? I don't know. And now I'm lead FPGA engineer in the Canadian-based Correlator team. So I've had, as Nicholas said, multiple roles, but I'm still on the same project. Started at AUT, then worked for the National Research Council in Canada, and now I'm freelancing, contracting back to the contractor MDA, who contracts to NRC to build this correlator.
MDA.
Yep.
That's a defense company. It's pretty cool, but we went to a meeting there even before your time, and you are welcome there for that mechanic arm that the space stations are using.
Yeah, the Canadarm. Yeah, they're working on Canadarm 3 for the station going around the moon. Yeah, cool company.
So these things happen from New Zealand. That's why I'm trying to highlight.
And yeah, after hours, this is what I do. I play a bit of hockey, do some coaching, fly gliders without engines, and a little bit of gardening. So if you want to talk about that, I'll talk all day about those things. But SKA is what I'm working on. It's the Square Kilometer Array Radio Telescope. They say it's one observatory, two telescopes on 3 continents. So the third continent is the UK, where headquarters is. And we've got a $700 million budget, which means we can only afford to build about 10% of the 1 million square metres of collecting area. So SKA2 in the future, budget, who knows, your guess is as good as mine, but there's 90% more collecting area to build. So why build SKA? Is it worth building a 10% version? This figure tends to say so. So down the bottom we have existing telescopes which are doing great science at the moment. There's the Jansky VLA, which is famous from the Contact movie. There's the giant meter wave radio telescope, which has had a recent upgrade in India. And there's the LOFAR telescope in the Netherlands that does very low frequency stuff, way down at 150 megahertz. And so SKA is supposed to do better than that. If we get to SKA2, it's a 10 or is it 100 times better again. So it is worth building a 10% system, and it will be a game changer for radio astronomy. Similar plot here, and this is talking about the survey speed of the telescope. So how fast can we look at the sky? And if you can look at more of the sky more often, then you can notice more changes, and astronomers like that. So everyone's very excited. So the first of the 2 telescopes is the low frequency array, which is going to be located in the Murchison Shire of Western Australia. It's going to focus on frequency ranges between 50 and 350 megahertz, so only 300 megahertz of bandwidth. But they're going to have 131,072, if people know the powers of 2, antennas out in the desert in 512 stations. So there's 256 of these antennas per station, and the distance between the furthest stations is 65 kilometres. So it makes it look like the dish it's replicating is 65 kilometres wide, which is huge. And out in the desert, if you went and visited, this is what you'd see. We've got these antenna things that look like Christmas trees, 2 metres tall. Pretty cool technology. This is a real photograph. The file is called DJI for some reason. So they've taken a drone shot, and there's another version of this file where someone's diligently gone through Photoshop and scrubbed out all of the people and the spare parts lying around. But the dust storm in the background is exactly the same. And this is the telescope that I'm working on currently. It's the mid telescope. We've got much higher bandwidth. We're going to do a 5 gigahertz band, or up to 5 gigahertz band in this range between 350 and 15.4 gigahertz. Some people want to go higher, but that's up to the analog electronics. We're going to have 197 dishes. So previously we had a nice power of 2. Now someone picked a prime number. I'm not sure why. Really frustrating as a computer scientist. And so we're going to build 133 new dishes, and then there's 64 in the Meerkat telescope. And this is going to have a 150 kilometre long baseline, and normally you measure these things in wavelengths, so at the high end this is going to be a huge telescope, high end of the frequency range. You go visiting and you see this. So yeah, there's a crane lifting one of the 15-metre wide dishes into place, and another beautiful landscape that is being put in. So they had a recent ceremony over in South Africa to thank the local indigenous people for the use of their land, which is fantastic, and the same has happened in Australia. And why? Well, to make beautiful pictures like this. This is what I care about. I'm not an astronomer, but these pictures are amazing. So there's jets coming out of a black hole. So radio jets, you can't see these things in optical wavelengths. There's top right is the remnants of a supernova, and that little thing shooting off to the left is apparently called the Mouse, and it's a pulsar that was probably the binary companion of the star that exploded. So it's being shot off into intergalactic space. And then bottom right with the false colours and grayscale, that's the centre of our galaxy. Interesting, I think. So the work I do is in the central signal processor, so it's the heart of the telescope. This is the correlator where all of the signals from all of the 197 dishes come flooding into the central signal processor, and we have to mash all of that data together. What does my next slide say? So we've got 100 gigabit Ethernet links from each of the dishes, and there's 197 of those. So that's 2.4 terabytes per second, 20 terabit, which someone said the other day was the peak of New Zealand's data usage in the pandemic. When was that? March 2020. Same sort of size. So we get 2.4 terabits in, 20 terabits in, and we have 640 terabits out of our correlator. So we reduce the data by only to a third. Here we go. Yeah. So 197 dishes, 2.4 terabytes. We expand that in the correlator to 3.5 terabytes a second as we oversample the data, and we get a little bit of bit width expansion, and we distribute that from our very coarse channelizers. Can you see? Yeah. So we've got a very coarse channelizer. So this is where we split out our parallelism to make it an extremely parallel problem, embarrassingly parallel. So we break the signal that we get in our 5 gigahertz of bandwidth, we break that up into 25 sections of 200 megahertz, and we distribute that to another set of processors, which is the frequency slice processor. So it processes 200 megahertz of bandwidth, which is this. Sorry for the poor quality. So a frequency slice processor has 20 FPGAs in it, and they're all interconnected with a mesh. So if you add up all of our networking, we've got about 30,000 fibre optic links within our computer alone, and they're all running at 25 gigabits per second. Results out, we send 33 billion complex visibilities per second, plus a bunch of metadata for each of those visibilities. to the science data processor downstream. So that sits in Cape Town. So here's a picture of our hardware for the hardware nerds. There's a custom Talon DX board. We have a Stratix 10 FPGA sitting in here, the largest one we can get with all its power supplies. We've got a whole lot of SFP cages down here, 2 QSFP cages for 100 gigabit Ethernet, and then these spiky things here are midboard optics, and each of those gives us 12 bidirectional fiber links. So there's 56 of them there, I think. And so that's what we use to interconnect all of our boards together. This is the board with its huge air-cooled heatsink on it, and we fit 2 of those into one rack unit, which is 2U high. Where are we going? So we're coming up to array release 0.5, which is sort of our minimum viable product with 4 dishes only. That'll be quickly followed by AA1, which is 8 dishes, then 64, and another year later, and then another 133 a year after that, and then we incorporate the Meerkat dishes. So the construction crew's lifting those dishes into place. They've got to build one of those a week for about 3 years. So they've got a lot of work to do, and it makes my job sound easy, I think. And then, in this picture, kind of interesting, these are where the locations of all of these dishes are going to be. So you can see there's 3 logarithmic spiral arms for each of these dishes. So when we correlate, we replicate a dish that is this diameter, so 150 kilometers across here. And then most of the dishes are in the center here in a sort of a random pattern, but they have these nice spiral arms. Yeah, it's very dense in the center. I'm not sure what. Yeah, I think, and they're slightly random, so you don't get the same length baselines in different places. Yeah, how radio telescopes work is cool, but I won't get into it. Right, so some problems, questions, and solutions. As an FPGA engineer, the correlated design is largely a problem in data movement. The DSP side of it, the signal processing, is relatively simple, still a challenge, but solvable. Actually moving the data around, getting the right data to the right place at exactly the right time so that we can multiply 2 samples together is quite a challenge, especially when we've got 500 FPGAs we're trying to do that across. We have to get all of the right samples exactly in the right place at the right time. And moving data is expensive. A few people have said that already. It's hard to do. So what can we do about that? Can we reduce our data rates? So do you need to send a full 32-bit floating point precision value across the network, or can it be a little smaller? And yeah, what precision are you just transporting that is therefore quantization noise? So I did a little bit of work on that, which I'll come to in a minute. And then we're streaming huge quantities of data. We're not storing it. We process it on the fly. So how can we do that reliably and efficiently through the design, especially from the correlator to our science data processor, which will be 700 kilometers further down the line than in the same building. So the current design actually says we're going to use UDP for that, and I'm having a hell of a time trying to convince the science data processor people to do something more efficient like RDMA. So let's go through some of these problems.
RDMA is?
UDP is, help me out, unreliable data. And RDMA is remote direct memory access, so sending blocks of data across a network so that it looks like they're together. So Nicholas asked for a provocative question. So here's my provocative question: is Ethernet too old? And yeah, sometimes. So Ethernet is great, everyone loves Ethernet, it works everywhere, but it carries a lot of cruft with it. Back from the days when you connected to the Ethernet by punching a hole into a coax cable. So there's interpacket gap, and there's a preamble to work out how fast your data is, and your packet has to be continuous on the wire, and you've got a small data unit of 1 byte. So that's all nice when you're running at 10 megabit, but we're at 100 gigabit, and we use star-connected networks. We're not trying to use a common medium, so that's not so great. And because we've got so many of these links on our FPGA, we went to put down a whole lot of Ethernet MACs to connect all of these FPGAs together, and there frankly wasn't a lot of space left to do anything. So great if you're making a network appliance, but if you want to do some science in your FPGA and not just move data around, then yeah, you've got a bit of a problem. So what I did was designed this new slim protocol layer, and cut out all of the stuff that we didn't need in Ethernet. So it's based on Ethernet, but got rid of a whole lot of stuff. So I used the same 64, 66B encoding and all of that. I use a 64-bit data unit instead of an 8-bit byte, so you can't send an odd number of bytes, it has to be a multiple of 8. Got rid of interpacket gap and preambles, not required when you're continuously signaling on the wire. And I've allowed idle words to be put anywhere, so if you don't quite have 25 gigabits rates, well then you just insert an idle word, which works nicely with FPGA buses and streaming data. So cutting out all of that stuff, we dropped the size of each of those links in the FPGA fabric from down to about 1/8 of what a 25 gig core would use. So yeah, does this go towards being absurdly cheap, Nicholas? Get rid of the cruft, move on, and make something that lets you do way more science. So how big are your numbers is a question I ask. So I did a whole bunch of work trying to work out, do we need to use 32-bit floats on this link between the science, between the correlator and the science data processor? And the current base design says we're going to use 32 plus 32-bit floating point complex numbers. And I thought, oh, that seems a bit much. Can we get it down? And I've succeeded in getting them to let me try 16-bit plus 16-bit, but I still have to support 32 plus 32 because they still don't believe me. And I think it could have been a 12-bit complex signed integer, and we would have been away laughing. So this little plot on the left is, so the worst case for our data is this blue line up here in mid, and the low correlator is down here below 8 bits required for the data, independent of what our signal to noise ratio is. So here we have lots of signal, but in reality we're operating down in this range for radio telescopes. Most of our signal is noise. There's not much common signal on each of the telescopes. Yeah, this is another way to sort of show it. This is receiving a visibility from our telescope. We multiply it together and work out what the common signal is, and then we accumulate or average that value over time. So I've got 15,000 averages here. We can see if we represent our data as 7 bits, then it's not good. It goes off into nowhere land. If we've got 9 bits or 8 bits, we're pretty close. 9 bits is still deviating a little bit, and above 9 bits, then we get the same answer as if we did everything with 64-bit floating point precision. So this is a little Python simulation I set up. And that still didn't convince people, so we did some more work, and we got an entire MATLAB model of the correlator and the science data processor, and said, okay, so if we quantize the data to quarter precision, then we get this blue line, so that's an 8-bit float, not much precision in it, and it still did a good job. When we go to half precision, then our error in our image that we get out follows very much what we'd get for single precision and double precision. So, yeah, ongoing battle, and eventually I'll win, but it's going to take a few more. So Anthony, what's his surname? I can't remember now. It's been a while. No, from from AUT, did this work with me. Anthony Griffin, yes, thank you. He's now down in Christchurch, still sort of working on SKA bits a little bit, I think. And then we have a problem with moving data a long way, and it's big data. It's 6400 gig links, and all of that UDP data has to go into a machine down there. And I'm trying to convince them that RDMA is the way to skip the kernel, go directly from the networking card straight into main memory, and then you can process it, sort of zero copy stuff. And people will sort of say, well, what happens when we lose some data? Will everything fall over? So we did some testing with RDMA. We set up an FPGA in the networking building at Rian's in Auckland on the North Shore, and that FPGA blasts out 100 gigabit Ethernet with RDMA traffic on it, and the traffic goes out through the network back to a server which has a Mellanox NIC on it, which does the RDMA into the server, and we had a program there to check that the data was correct. And we set this up. Rian's provided some nice server equipment and 100 gigabit network to test on, which we did for an hour in March 2020, and we sent the data all the way from Auckland to Multicore World 2020, did that happen, in Wellington, and turned it around and sent it all the way back. So it took a 1,200 kilometre round trip to Wellington and back, and we didn't lose a single packet that entire test, which was incredible. So here's the weather map for the Rian's network. It's digital twin, I don't know. Auckland is here, NSH is North Shore, Frankton is where I live, so I went past my house, all the way down to Wellington and back again. And if you can read those numbers, it says 96.5 gigabit per second of throughput, and we ran that for an hour, so they dedicated that link to us, which was awesome. Really good working with Rian's. So looking to the future, I've got a few questions to look at. Are posit numbers a good idea? John Gustafsson, has been pushing that hard. I'm quite a fan. I've started working on a VHDL library to do posit number stuff so that we can test this. And we've also, on the back of all of this work we've done for the SKA, picked up work to do an ULMA correlator upgrade. So ULMA is the correlator in Chile at 5,000 meters high. Does some great work, but they want to expand their bandwidth from 5 gigahertz to 60 gigahertz of bandwidth. And then the NRC has been selected by the NGVLA telescope, which is the United States answer to the SKA, to build the correlator for their new telescope, which will have 256 antennas across America. So our design is going to influence that one quite heavily, I think. And then, of course, there's SKA2, if we can find the budget for that. And it will have a 20 times maximum baseline length, so there'll be antennas in other nations in Africa, up to the top of Africa, so there'll be 2,000 kilometre baselines, which will start to rival the Event Horizon telescope that took the picture of that black hole that we saw in the previous presentation. There'll be 10 times as many dishes, so N is 10 times, and the amount of computation in a correlator and generally further down the line is N squared, so there'll be 100 times more compute. So we're getting up into the exascale size of things. Yeah, so that is me. Thank you very much.
Fantastic.